Right, so anyone out there? Welcome to our session on T-tests, the final one, the final frontier. Oh dear, the numbers are going down dramatically. Do you have any assessments looming? No. It's just Thursday.
It's just Thursday.
Just Thursday, yeah. I know exactly how you guys feel. I'd like to be somewhere warm now. I swear to God. Good afternoon. I swear to God, my cats have wet paws now. Good afternoon. It's going to be my catchphrase, hey? Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Oh God.
It's not a good day today. It's so
Why is it
rainy.
not? Look, there is no such thing as bad weather. It's just unsuitable clothing. Good
I
afternoon.
don't think anyone could dress suitably for this because you're going to get soggy.
Well, look, if you are a duck, you love it. You just put things into perspective. Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon, Ryan. Nice to see you on the chat. Seems to be my catchphrase. Good afternoon. Good afternoon.
I don't even know what time it is.
Sorry?
Don't even know what time it is anymore.
You don't know what time it is? Well, it is 4 minutes past 12.
Okay.
And it is I think, Thursday the 5th of March in the year of our Lord 2020.
Okay.
Do you need to know where you are?
No, I know that much.
Oh, God. Wow.
Drink that much.
Wow. Usually my problem is not what time is it or where am I, it is more who am I and how many of them. Right, let's make a start. Because I want to have lunch. That's a very strong driver for me. So most wonderful, good, whatever, afternoon. Please don't forget to do the attendance thingy. I was just thinking, it's a good thing that we don't do any paper attendance because it doesn't look good. There is probably a reflection of either my teaching or the topic, which I fully understand, but. And as I said previously, the quizzes on Moodle are, not on Moodle, the quizzes on my website are open. If you have, and all of them are open again, can't remember when the deadline is. 15th, no, 24th, somewhere in April, I think. And if you have not done them, please do them all. If you have done the certain quizzes already and you are happy with the score, you don't need to do them again. That would just be occupational therapy, and that's not something that we are really looking into. Right, so plan for today, I really want to get rid of these T-tests because life is too short. And let's move on to then something different. But as I said, let's do the T-tests first. And let's wrap them up. And also, because you need them for one of the quizzes. People always ask me, in the exam, we are not going to have access to Excel. What are we going to do? Trust me, I'm aware that you don't have access to Excel, so I will not set any questions that requires you to have access to Excel. And I know Excel is love and Excel is life, but don't worry about these things. It's been taken into account. Okay, so when it comes to T-tests, T-tests are very, very useful when we want to compare samples with each other, and the prerequisite is that these samples come from populations that show a normal distribution. And I showed you, for example, what we can do if we want to compare two samples that are totally independent from each other. So we have a sample 1 and a sample 2 with some data. And I deliberately draw it like that because the number of data does not have to be the same in sample 1 or sample 2. It doesn't matter if these samples are totally independent from each other. So if you take blood samples from, let's say, healthy and not so healthy volunteers, might be a different sample size. And the basic of the T-test is we do not compare the means of the samples with each other. Instead, what we do is we say each sample comes from a population, and instead of comparing the sample means, we compare the population means with each other. And that is the principle for T-tests. Now, some people have asked me, what happens if you have not 2 samples? What if you have 3, 4, 5, 6 samples? Can you still do a T-test? The answer is, unfortunately, no, you can't. Technically, you can't. Technically, you shouldn't. There is another test that you can use if you have more than 2 samples. And this test is actually called analysis of variance, or, because nobody can say that, especially on a Thursday after Wednesday, the abbreviation for that is ANOVA. You can do an ANOVA if you have more than 2 samples to compare with. We're not going to do that here, and I'm not showing you. There are lots of YouTube videos out there that actually show you how to perform an ANOVA. But in our case, in the case of the T-test, we want to compare the population means from the samples that we have, because the samples sort of tell us about the population. And before we start anything, before we get really wild with calculations and so on, we formulate a null hypothesis and an alternative hypothesis. So the null hypothesis in this case would be there is no difference between the 2 population means. And we can write this as mu1 equals mu2. The 2 population means are the same. This implies that the 2 populations are the same. This implies that the 2 samples are taken from the same population. This implies that there is no difference between the 2 samples and the population. So it's from one population. You sometimes see that in a slightly different form. You sometimes see this as mu1 minus mu2 equals 0. I got a few. Okay, good. Hello. You see this as mu1 minus mu2 equals 0, which is basically the same as mu1 equals mu2, right? So this alternative hypothesis says there is no difference between the 2 populations. And obviously, the opposite, what you would get is the alternative hypothesis. And in this case, we have different options. What did I say? We have different options. We just simply can negate the null hypothesis, and we can say the two population means are not the same. That is one way of forming the alternative hypothesis. This just simply means that, well, the two samples are, the two populations are not the same. That means the two samples that we have come from two different populations. And that implies that the two samples are statistically significant different. So there is a difference between the two samples, whereas under the null hypothesis, it means there's no difference between the two samples, or not a difference that we could actually really prove that there is. Sometimes, not very often, you also see a different null hypothesis, a different alternative hypothesis, where you are more specific in a way. A valid hypothesis could also be that one of the population means is larger than the other. And I've written it here that mu1 is larger than mu2. It could also be the other way around. And depending on how you formulate your null hypothesis, it has an influence on how you your data. So depending on the alternative hypothesis. Here, we just simply, for the first case, we just simply say we want to know whether our two populations are different. And when we look at basically a normal or t distribution, we just simply say, right, we want to know, is it different? So is it either in this range or in this range where we see a difference? Because we go to both sides, this is called, this kind of alternative hypothesis would ask for a two-tailed test. Because we have got a tail here and we've got a tail here. So if we say the two population means are different, then we are going for a two-tailed test. If we go for something like that, what we want to know is we are just interested if one of our, if mu1 is larger than mu2. We are only interested in one tail. We are not interested in whether it's smaller. We just hypothesize it is larger. And therefore, we are only interested in this part here, and therefore it would be a one-tailed test. Okay? So, before we get started, we have to formulate our null hypothesis and, more important actually, the alternative hypothesis. And then we have to set a sort of a criterion, a limit. Where do we think that things start to be different? How different do they have to be? We can say we believe they are different if, for example, we get a p-value of, and we can set it at any level, but if we say, for example, very often in science, we said we want to say, yes, they are different when they are at least, say, when they are less than 5% chance that we get them if the null hypothesis is correct. And we said this is our significance level alpha. In the case of the one-tailed test, alpha is just simply this area here, that's 5%. In the case of a two-tailed test, alpha, this 5%, or whatever value, it's up to you what value you want to choose. You can set 1%, you can set 0.1%, you can set 10% if you like. It's up to you. But in the case of a two-tailed test, alpha is distributed between the two tails. So actually what we are looking for is 2.5% here and 2.5% here. Okay? My advice would be, whatever you do, and unless somebody really, really, really forces you to do so, do not go for one-tailed. Always go for two-tailed. Because realistically, what you want to know is, are these two samples the same? Do they come from the same population, or don't they come from the same population? That's all you want to know. Everything else is fuffing around and makes things more complicated. Okay? Now, I showed you how we can do that in, for example, Excel. We can calculate a p-value. And the p-value tells us about the probability that we get this result that we observe if we assume that the null hypothesis is valid. If we get this result, if our p-value, for example, then is smaller than our exclusion, our alpha, we know that it is really unlikely to get this result if the null hypothesis is correct. So what we do is we just simply say we must reject the null hypothesis. So p smaller than alpha, reject null hypothesis, accept the alternative hypothesis. If p is larger than alpha, we cannot reject. The null hypothesis, but we can reject the null, the alternative hypothesis. And that's that tells us if our p-value that we get is, say, 10% or something like that, and we set our limit to 5%, then 10% is larger than 5%, and therefore we cannot reject our null hypothesis. We cannot say that the two samples come from different populations. They could come from different populations, but we just simply don't see it. I showed you how we can do a two-sample t-test. Two-sample t-test. If the samples are independent from each other, And here the Excel equation is just simply, you can do that in Excel quite nicely, equals t dot test. And then it asks for 4 different parameters. This is the sample data of 1, sample data of 2, it then asks you how many tails do you want to test. And as I said, I would always go for number 2, 2 tails. And finally, it asks you what kind of test you want to apply. And I told you for a 2-sample independent test, you always want to apply what is called the Welch test. And in Excel and in Google Sheet, this has the number 3 on it. And depending on the p-value that you get, you will see, yes, it is smaller than alpha that you have set. And if that is the case, you reject the null hypothesis. If p is low, h0 must go. Okay, does it make sense? I also showed you, so that was a 2-sample t-test with independent samples. I also showed you a 1-sample test where we just simply have a sample with data, and we want to compare that to a reference value. Now, I didn't show you actually how you can do that in Excel, because Excel doesn't have a built-in function for a 1-sample t-test. But you can play the system a little bit if you know the trick. What you can do is you can say, right, this reference value actually also comes from a population. So we know that the sample comes from a population. With a population mean. What you can say is, I just simply pretend that the reference value also comes from a population, which is characterized by another population mean. And what you then can do is you can create your second population just simply by putting in, how do I do that? So here we have the sample data. And what you do is, next to it, you put in the reference value. And you repeat this reference value at least one more time. So what you basically have is the sample, yeah, that's okay, that's clear. But now you have sort of a mini population that consists only of of the reference value twice. Now, if you calculate the mean of that, of course, it's the reference value because it's 2 times the same thing, right? The standard deviation of that would be 0 because there's no difference to the mean of it. And that is exactly what you want in this case because we don't know the standard deviation of our reference. And remember, we do t-tests only when we have population, but we don't know the standard deviation of it. And what you can do now with that is you just simply do your 2-sample t-test equals t-test. Here the sample 1 data. Here, for the second part, you highlight the cells like that and treat this as your sample 2. Then you say, I want a 2-tailed test, so that would be 2. And I use the Welch test. And remember, we use a Welch test when the variances are different or when the sample sizes are different, or both. So 3. And this will give you then a p-value which tells you whether your sample is statistically different from the reference value. Yeah? And I really want you to try that out when it comes to some practice calculations. We also said if we see that something is statistically significant, if our p-value is smaller than alpha, we can check whether it is really statistically significant or whether it's just, it doesn't matter in practice. I mean, for example, I know an astronomer once said, I know the surface temperature of the sun is 50,000 degrees, but I forgot whether it's Celsius or Kelvin. It doesn't really matter in this case because it's so big. So in this case, it would not really matter, but sometimes if you say, today, the temperature outside is minus 100 degrees. No, the temperature is 50 degrees, let's say. The temperature is 50 degrees outside. It doesn't matter whether it's Kelvin or Celsius. In one case, probably in both cases, you would be dead. If our p-value is smaller than alpha, if we see that there is a statistically significant effect, we can do a Cohens D. The effect size. In the case of a 1-sample t-test, it's fairly straightforward because what you need to do is you take your mean of your sample minus the reference value, and you only take the positive one, so that's what I indicate with that, and you divide it by the standard deviation of your sample. And if that gives you something that is larger by convention as 0.8, we would say there is a massive effect. In the case of 2-sample test, independent, just make a little bit of space here. We can say Cohens D, effect size. We can also calculate that. We just simply take the difference between the sample means and divide it by the average of the two sample standard deviations. And again, if that gives you something that's larger than 0.8, it's massive. Happy with it so far? Yes, you can do it. Easy. Now, if you paid attention to what I've said, you noticed that I frequently said we have a two-sample t-test. And I always emphasize the word where the samples are independent from each other. So that probably indicates to you that there might be a two-sample test where the samples are not independent from each other. So this would be a two-sample dependent t-test. And because people like me can't spell dependent without major accidents usually, it's also known as a paired sample test. Paired sample t-test. What does this mean? In the independent case, we said, well, the two samples don't have any link with each other. In the paired test, what we usually do is we have sample 1 So for example, I take a blood sample from somebody here. I then do an intervention. For example, I give you chocolate then. Yeah? Would be good?
Yeah.
Good. So I take blood sample here, then do an intervention. And from the same person, I take the blood sample again after the intervention, after the chocolate. So what we have here is a typical before and after scenario. So we have before the intervention, after the intervention. And I do that for a number of other people. So these samples are linked. They are linked through the person, right? So they are not anymore independent from each other. So for example, we do a weight loss drug. So patient 1 starts with 102 kilograms and after the treatment has 95 kilograms. Patient 2 starts with 88 kilograms and after the treatment has 89 kilograms. I think there was probably some pizza involved in the middle of the night or so, right? Because I didn't do a lot. The next one is pretty good, 145 to 122 afterwards. Yeah? So you see the concept of a paired test. We compare the two samples with each other. And the way you can do that is you have two different options. What you basically can do is you can, in option 1, What you can do is you just simply calculate the differences between the individual samples. So 102 minus 95, that gives us 7. 88 minus 89 gives us minus 1. So here you have no longer the real weights. What you're looking at is the differences between the two samples. So here you have a new, if you like, a new sample with the differences. So that's a new sample. And what you really want to know is there a difference between these differences and basically 0? Because 0 would mean, well, they didn't lose any weight. And therefore, what you can do is you treat this as a one-sample t-test again. But this time, your one sample is the difference. And as you can see, I have done this little trick here. I just simply say this is my reference value. And with that, I can do my t-test. And lo and behold, look at that. I've done it before. P equals 0.1226, so 12.3%. This means I have my probability to get these samples here, to get these differences, is 12.3% if the intervention, the drug, is not effective. And if I said I want to know everything about everything less than 5%, I would say, well, should I invest in this drug as a company, for example? No, it doesn't look very effective to me. Forget it. Next. Yeah, I would not invest in this drug. I would not take this medication because it apparently doesn't have any statistically significant effect. Yeah? So what you do is a two-sampled paired test. You can calculate the differences and then compare the difference to 0. It's just a modification of a one-sample t-test. Because this is so frequent and people use it so often, in Excel there is a function for that. And you don't have to learn anything new. You use the Ttest function. You put in the data for sample 1. You put in the data for sample 2. You go for a two-tailed test. So far, nothing new. And then you tell Excel, please do a paired t-test. And in Excel, paired t-test carries the number 1. That indicates a paired test. So 3 is for an independent test, 1 is for a paired test. 2. What did the Lion King say to little Simba? We don't go there. 2 is basically a t-test, but where the samples have the same variance. Just don't touch it. It's not worth it. So either 1 or 3 in this t-test. How can we do a Cohens D for that? Effect size, Cohens D. Well, we use exactly what we have done for the one sample t-test. What we do is we just simply take x bar, the mean of the sample of the differences. So we take the mean of these differences here. That's our difference sample, if you like. That's the mean that we take. We take away 0, that's our reference value. You don't really have to write that down, because that's the reference value in this case. And we divide it by the standard deviation of the differences. And again, if that is larger than 0.8 by convention, this is considered as a massive effect. But you only do that if you find that if the value that you get is smaller than your significance level. Otherwise, it just simply doesn't make sense, because what you're basically saying is there's no difference between the two samples, but the difference is massive. Does not make sense. So you do that only, you do Cohens D only if you find that there is a statistically significant difference. Okay, happy with that? So what you can do now is, well, you should be able to look at two samples, make a decision, are they paired or are they not paired? Are they independent? And usually what you will find is, as I've outlined here, if it is paired, you have a sort of an indication where it says, for example, patient 1, patient 2, patient 3. So you see that these things here are all relating to the same patient. So you very often have this extra column there where it numbers the patients. Or it gives the observation a sort of a numbering, so that people immediately see, aha, these two things belong together. So you need to be able to make a decision. Is this a paired, or is that an unpaired, an independent sample? And conceptually, there is no difference between a paired t-test and a one-sample t-test. Just that in the paired t-test, what you do is you calculate the differences, and you can do that either by hand, like I've done it here. You calculate the differences and compare that to 0, or you let Excel do all the hard lifting, and just simply use the correct sort of numbering in Excel. T-tests. I can tell you that this will follow you as bioscientists to your grave, because that is the standard testing for basically anything that you do. Unless you have more than 2 samples, and again, that is something for the ANOVA. The basic principle of an ANOVA is a slightly changed null hypothesis, where you just simply say population mean of sample 1 is the same as population mean of sample 2, is the same of population mean of sample 3, is the same of population mean of sample 4, etc., etc. And an ANOVA will tell you if one of them is not the same. At least one of them. It's not going to tell you which one it is. As I said, there are lots of YouTube videos out there. Don't stress about it. I'm not going to ask you ANOVAs. Any questions? If you've got any questions, I'll hang around a little bit, or hit me up on the group chat, or DM me. I'll try my very best to answer. Thank you very much. We are done with T-tests. Yes!